Okay, so the two sections that we're going to be doing, one is sample prep and the other is just getting to know the SEM. Serena is doing the other group there, which means you folks get to hang out with me, and we're going to go through as many versions of how to think through sample preparation for an SEM as I can. We will go through some of the basics. We have at least one weird sample person, in here, which means that you're also going to get to see me try to figure out a challenge because I've never done some of the stuff that she wants to work with either. But that doesn't mean it's impossible. It's going to be interesting to try to figure that out following, some general guidelines. And I think this is the set that, in terms of sample prep, these are the questions you always want to be able to answer with some amount of knowledge of what the SEM is doing and what it is you've got. It is, okay, what do we want to actually do with this material? What is the goal of our analysis? That's the overriding question that we want to get. Okay, it's BP, right? Mind if I use you as the example since you've got the weird stuff? All right. Let's take that stuff that's in a liquid, okay? What is it that you'd want to learn about or measure with that? Okay, so a key question that I'm going to single in on out of that is the phrase, when it's drying. So are you asking us to try to have this as a liquid droplet in the electron microscope?
No.
Okay. So see what we kind of did there, okay? Now, nothing that we necessarily did wrong, but we're trying to make sure that we know what it is we want to put in the SEM and what we want to do with it. Because if I want to take an organic compound and put it into the SEM and then catch it in the act of drying, there are probably, I guarantee you, there are electron microscopes in the world that could be built to do this. If you want to catch a time-lapse video of something, that could be specific software to capture time-lapse videos. That could be a specific SEM design where we want to limit contamination, so we make sure there's a cold trap in there. Analyzing it after it's dry is probably a little bit more easy. Can you describe what the material is a little bit better for me?
Sure. So we in our lab produce gold.
I'm familiar. Yeah.
And so then.
Okay. So since the speaker's on here, they're working. The person I have speaking is working with tholins, which are basically they are kind of complex organic like goop. Can I use the phrase goop and not be offended? Like, anything I say might get back to her advisor. So organic goop, and it's generated out in space by interactions with the space environment, by interactions between atmospheres and surfaces. There's probably a lot of ways to generate the stuff. And they've taken this material, reacted it with water, reacted it with ammonia, scraped off the solid components, and so they have the in solution components. They're going to precipitate that out, and that's presumably going to give us something that's like a precipitated, sugar-like structure or something along those lines. And well, that means we're probably going to be looking at a precipitated compound that has some amount of crystal structure. It's going to be an organic material. It's going to be tough to analyze anything in the chemistry about that on a standard SEM, but that might mean we can still get something about the structure or patterns of crystallization or anything else like that out of this, okay? So notice what I'm doing here. I took the example of the weird sample, no offense, that we have out of the group and said, okay, let's start running through what can we analyze, what would be a real challenge. Let's make sure we understand the properties, and then start getting to what will the analysis that we do actually get us. Okay, so prior to SEM analysis, you have to do some version of a step to assess what it is you want to analyze, because there are plenty of combinations of materials and analyses techniques that will either not get you an answer or will actually potentially damage your system, which is particularly bad. And if you don't do this assessment, the downsides can be a damaged SEM, which, you know, is a $100,000 instrument at the minimum, or a paper that's rejected that you spent a lot of time on. And I've had to reject things before where people tried to put SEM analyses into something that they couldn't do, and it wasn't capable of doing what they wanted it to do. And when you say, this is a fundamental issue, your SEM is giving you a data cloud that's not actually telling you anything about your sample, that means, you know, that's a bad thing. You don't want to waste your time on that. So assessing what you want to know about your material, what's the best way to do that analysis, and then how do I get the sample into a state where I can do that analysis is the set of steps I'm going to try to make us think through. Okay? And if we don't do this, we may just get a terrible image. We may just get a data table that gets a paper rejected. We may not get an alarm when something is going to go wrong. Now, sometimes there may be alarms. That is also a bad thing. You don't want to trigger the alarms. But that's what we've got to think through here. All right. So we already did this with the solution sample, so we'll leave BP out for this one. Okay. Somebody else, name some stuff you might want to analyze in the SEM. Describe material for me. We'll start up here.
I mean, I've heard like kind of
Cool. Excellent. Okay. Rocks and minerals in various forms. Cool. All right. Crystals works for me. Okay. Let's go to the folks over there.
like an inception.
In section. So we're still on rocks and minerals here. What else we got?
I example that rocks, parallels, and melodic features and textures, and also the complete.
Okay, organic matter. Boom. All right. Can we do a composition on organic matter? Well, the answer is going to be no. We can't really do that. That's actually a full limitation of our pretty much every SEM. We'll talk about that more tomorrow in the EDS session, okay? Because we're just doing sample prep focus right here. I have a list right here of what our rules are, okay? Material must be able to be put into the SEM. It must be stable enough under electron bombardment, meaning it can't be a compound that's going to break down if I fire electrons at it. It has to be stable under vacuum. So you'll notice I started addressing with BP is this going to vaporize while it's under vacuum? Is it going to boil? Because putting something into an SEM thinking I might get a sample and having it boil, your sample is not going to stay where it was. We're going to have to spend a lot of time avoiding significant charging because this will affect any analysis that we try to do. And whatever the signal is that we're after, we must be able to get that signal out of there. Not every material will produce a strong response in every detector. Organic and biological materials would be a bad use in an EBSD or an EDS because we're not going to get a signal out of it. Okay? Here's my list of different sample types. This is a good breakdown because each level on here has its own suite of sample preparation that we might want to do. Metals, solids that are dry and inorganic, solids that are organic, synthetic polymers and biologics, and the terrifying stuff, liquids and wet samples. Terrifying because they will flat out boil. And that will mean that, they will be active during the sample, as well as potentially contaminating the equipment. Analyses that we might want to do on that set of samples, we can then group into this set. Imaging for something about the shapes and textures. Imaging to be able to pick out one phase from another. And then X-ray or other types of measurements for compositions, mineral identity, and orientation. So we've got that set of materials and set of analyses that we might want to do on them. And not all of them will work on every material, but let's go through how to get there. First question, how do I fit this into the SEM? Well, sample size actually matters here. The largest SEM on Earth is pictured there at the right. If you need to analyze a very large chunk of material on an electron microscope, that is the largest known scanning electron microscope right there. We mentioned during the morning session that it's worth thinking about the detector positioning, because certain responses will be stronger or weaker depending on those. Most electron microscopes can fit a sample that's, a couple of centimeters across. It can be limited in height. I can fit a chunk of rock this big into our SEM and be able to get it in there. If it's too big, it won't fit in, unless you have something like that. Most SEMs will have something like this as a setup for a sample holder. When you get into ours tomorrow morning, you're going to see something that looks like this. This is a version of the stage that we put in. It is, this big, and it has vertical motion of about 5 to 8 centimeters. So if your sample could fit in that box, you could put it into our SEM. These are different sample holder designs. A great number of both electron microscopes and microprobes are rigged with something like this, where either a 1-inch or 1.5-inch round disc can be stored in them. This can be done with thin sections, because many thin sections can be prepped on 1-inch round glasses, or you can literally take a chunk of your material and get it into a shape where it is prepped and at a 1-inch round size. Over here, we have other types of sample holders. This one is built for a standard thin section, the rectangular ones. Suddenly I forgot the word rectangle. I need more caffeine. So you can literally load your rectangular thin section into this, prep it in that state, and that would hold it. This was a piece of a pottery shard being loaded onto a rough stage to fit into an electron microscope chamber. Now, once we're in the electron microscope, we get to the next step. We fit our sample inside. We need the material to be stable under vacuum, to respond the way we want when we bombard it with electrons, to produce a signal, and have that signal be able to reach the detector. So here is a secondary electron detector. Here's a BSE detector right built into there. Here's a couple of other detectors off axis. This one is almost certainly the position of the X-ray detector. Just to illustrate, let's think about our shard here. Let's say the spot I wanted to analyze was right there. I have a ridge that's elevated compared to that spot. If I'm trying to get onto whatever this coating is here, as opposed to the ridge, it's going to be a challenge, because what happens if I load it into my SEM and the ridge is running along here and the spot I want to analyze is on this side? Well, now I've blocked my detector from the rough spot that I want to analyze. All those types of things are things you have to think through while you're mounting stuff. Next, to get material into an electron microscope, it must be somehow secure. When you put it in, even on ours, the first thing that's going to happen is it's going to go from being at 1 atmosphere to being at 1 times 10 to the minus 5 atmospheres rather quickly. That's a big wind. That air has to move somewhere. Air moving, if a particle is loose enough, can move material around. Air is not the only thing that can move stuff either. The electrical environment in an SEM can cause material to move as well after the vacuum has been started. So we're going to need to find ways to anchor things. Any electron microscope will have some version of a metallic conductive stage that is linked to the electronics of the surroundings and grounded so that this stage will be a part of carrying away any charge. So it'll be part of the electrical system. Some solid materials you can lay, if I have that chunk of pottery, I can just literally put it on the stage. It's not going to move in the wind, and it's not going to move electrically. If I try to tilt the stage, that could be a problem. We'll see why we have to do that at another point. But a lot of mounting done in an electron microscope is done on these little sample stubs. And I think a couple of you have seen these before. One of the samples that we had earlier that we sent down the hall was already mounted on sample stubs. There are various sizes. The most common, I think, is easily the 12 millimeter ones. And you'll see a bunch of these down the hall too. They have standard backs, so they will fit into holes that are available. I think manufacturers have all just kind of figured out that, yeah, let's just make these all the same size. That this is much easier if every manufacturer does the same thing with the size here. Because the thing you might actually want to customize could be the sample holder. And there are, this is a good example of how many different shapes and sizes and versions of these you might come up with, depending on what the shape is and size of your material. They can be modified. You could, hypothetically, if you needed to analyze something fibrous, you could literally drill through it so that you have a hole that you could hook your fibers around the thing to keep it in contact and keep it there. Most of them are probably aluminum. You get copper and brass a few times. You get stainless a few times. You can buy different designs if you're really creative. There are tiltable ones hidden beneath the sharing thing up there. You can get a lot of versions of these, okay? If I just put a loose powder on one of these tabs, it's a loose powder. It can still go flying, especially if I'm tilting the thing at an angle. It is also going to be put under vacuum. I don't particularly want my sample to vanish when it's being put under vacuum or to send material into the vacuum system of the electron microscope. There is different ways to connect things to these tabs. There's some versions of organic solvents that are sticky. There's a list right there, okay? This one is literally go to a hardware store and buy a tube of super glue. Sometimes a fix works out. You will see down in the microscope lab, we have two options ourselves. There are paints that include some amount of either carbon or silver or other similar dust in an organic solution. And you can use this as basically almost an organic glue, where it's conductive because it has carbon or silver in it. We have, I believe, some carbon paint down in our hall. Could be silver, I honestly can't remember right now. The other common thing you'll find is double-sided tape. And we had a question about this earlier. Conductive tapes are perhaps the most common here. There's a set of them right there. Double-sided tape impregnated with either aluminum or silver or copper or carbon have the nice benefit of attaching to your sample and helping you carry away charge. You could also use, Jello, gluten. I've had to mount stuff in Play-Doh before. I mean, it's a thing. You get creative. Okay, so we've got our material. Now we want to put it into the SEM, and we're going to bombard it with electrons. The other thing that we have to anticipate and be ready to deal with is the electrical response. When we fire electrons at our sample, we're going to build up a charge. If the current cannot be removed, charge begins building up. This will affect both our material and our ability to get data from that. This is a powder that has begun charging. The bright area is gaining extra electrons from the fact that there's a beam of electrons firing at it. And those electrons are basically, they're just glowing back at us. The whole sample is now glowing because the whole sample has become an electron emission source. Here's that same powder when it is not charging. So now we can actually see the texture on the surface here. Another thing to highlight, to think about is, if we're working with a finely powdered or finely grained material, if this material develops a negative charge and this material develops a negative charge, they will want to move apart because they will begin feeling each other's charge. An image over an area can take, on ours, you can do, the most common image duration is 30 seconds to acquire. So let's say I have two samples, two pieces of material that are sitting there. They begin charging. During the 30 seconds that I'm scanning to take a photo, they push themselves apart and one of them moves. Now my photo's ruined because the material has moved mid-analysis. One that we actually had to deal with an intern this summer while practicing is, what happens if one of your pieces of powder is particularly valuable? Let's say you have loaded a single pre-solar grain that you checked out from NASA on there, and you don't anchor it very well because you don't want to lose your grain, but now you develop a charge and the sample starts moving. And you can lose grains like this. They could be lost in the sample chamber. Typically, before you load stuff, it is good practice to blow some compressed air over a sample. Because if your material is not super important, like you've got some random powder that you attach to a piece of tape, a bit of compressed air will help verify that it's unlikely to move, because anything that has not been well attached will probably blow away, as long as you're willing to blow stuff away from your sample. All right, let's see a little bit more of charging. We've talked about charging being able to move stuff. Here is charging affecting our image quality. The horizontal stripes that you see in this image are charge building up and going across the sample. So here we're getting, I don't know, like the SEM is a scanning instrument, so it's literally stepping down and scanning across with a certain amount of dwell time at each pixel. So if you're building up a bit of charge at one spot, as it scans across, it sees that, and you get this horizontal banding matching the scanning pattern. Obviously, this is not a publishable image if you have this amount of charge buildup. This was a fun one. This was on our SEM. This was done about a month ago. One of our postdocs here wanted to do an image map over their sample, left it running for 9 hours overnight, and so this is a grid across it. This is the image quality that they got out at the end. It is poor. When you zoom in, there are features that are completely misaligned. There are many areas that are just not able to focus on, and the horizontal stripes and different changes in contrast. This is a buildup of charge. This basically wasted 9 hours of analysis time. We had to redo this map. The other thing that's happening here, when we go in, we find that these frames are not lining up very well at all. They'd do one frame here, and then it'd repeat the same part of the image and do another frame, so it wasn't able to stitch it. What was it doing to cause that? Another of the effects of charging is actually rather interesting. Okay? If my material is charging, and I'm shooting a charged beam at a charged surface, as the surface builds up a charge, the beam begins to move in response to the charge. You may not always see the horizontal banding as the effect of charging, even if it may be there. Beam deflection is a common response to charging. This may mean that if you try to do an image mosaic like is done here, that one frame and the next frame don't line up because as it moved across, it was deflecting in different directions from the charge. The other symptom of this that you may see is that you focus nicely on an image frame and suddenly it seems like your material is moving. So, my image seems like it's drifting downwards. Well, why is it doing this? It's not actually necessarily that it's moving. Well, it could be. But more likely is it's building up a charge, and so every time it scans across, the beam gets deflected a little bit more. And that makes it look like the frame starts moving. So apparent motion on a screen is often an effect of a sample that is charging. Stick that one in the back of your head. You may not see it again the rest of this, the rest of the section. You might. We put an uncoated material in there. Horizontal banding, areas that are glowing, those are obvious signals of charging. Why the heck does it look like my sample is moving? Is my sample not anchored properly? Probably is anchored properly. It's probably charging. That might be why you'd see a sample starting to move. Those are our hints of charged material. Now, let's start actually thinking through sample prep. Here is an image of loose material in an SEM. What can you folks tell me about this material or about this image? Okay. First question. What type of image is this? Correct. Everybody here? Where it says in the table, it's a BSE image, it's a backscattered electron image. Okay? It's a backscattered image on a powder, which means that if we look in some of the down areas and some of the sides, why is this a degraded image right here? Well, we're not focused on it, first of all, but also it's a backscattered image. So if it's at an angle, it may not give us the best response. Okay. Is there a difference between one type of material and the next? PP, you're nodding. What do you got? You're correct.
Well, there's like a background.
Okay. There's a background. That's probably what it's stuck to. That's what I wanted you to get. Here's a darker material. Here's a brighter material. Okay. This is labeled as debris from pump. Okay. I found one that I liked from this. Okay. This is on a powder. It's backscattered electron imaging, backscattered imaging on a powder like this is still going to try to show us compositional contrast. If we did secondary electron imaging on this, we might be doing a better job of looking at the shapes of this. BSE imaging on powders is doable, but it is also tough because we have two signals that are trying to show up. One of which is this material and this material are probably different. One of which is this material and this material are probably the exact same material, but this one is angled so that it's giving a stronger signal to where our detector is. So even though these are probably the same chunk, same thing right here, these areas are brighter and darker on single pieces just because they're angled to give the response to the detector. Okay, so we might get usable information out of this. It might not be perfect because if there was more than one mineral as part of whatever this sample is, I have no way of telling you right now because I cannot distinguish by looking at this whether this is the angle that we're looking at or whether there's actually a different material in there. I have two different signals put in together. If, on the other hand, rather than looking at the material like this, I processed my stuff into a more solid state, that could give me a much cleaner signal and allow me to assess what the stuff is that each is made of. We've only briefly mentioned EDS. EDS is the same way, that for a good EDS analysis, I need to have a strong signal return in a certain direction. If I try to do an EDS analysis right here, I may get a signal, or I may not, depending on which side of this little ridge I'm on. So let's say we wanted to do a good backscatter image, or we wanted to do a good EDS analysis on that powder. Well, what do we do to this material to get it there? The most common thing to do, and you saw some of these in the sample mount image that I showed at the beginning of this session, is you take your material and embed it into something that's going to make a solid bond with it so that you can flatten it into a cut, shaped, and polished surface. The rules for what your embedding agent must be has to be low enough viscosity, because if it's too sticky, it will never surround your material. It has to be able to firmly attach to the sample. It can't chemically or structurally interact with the sample. It has to be stable in the electron beam and relatively available and cheap enough that nobody's going to care if we buy the stuff. Because if it costs $10,000 to buy a bottle of something, you're not buying it. Not for this purpose. There formerly, on old samples, was a molded, chemically resistant plastic called bakelite. It's not commonly used anymore. You may run into this if you're dealing with old enough samples. Almost everybody will, for this purpose, use some amount of epoxy and a hardener. Epoxy is an organic compound that, when mixed with a second substance, undergoes a chemical reaction that turns it into a solid. That means it's low enough viscosity, you can pour it over your sample, it's cheap, and you can polish it up and treat it as a solid afterwards. Epoxy is typically non-conductive. It is an organic molecule. So it's going to be a low Z number when we go to backscatter. It's going to be pretty dark. There are conductive epoxies that exist. If you are really caring about a certain organic compound sample of a tholin, and you need a real good image of this stuff, and you just can't afford to coat it because the material is carbon-based, like a tholin, so I'm going to mount it up, but I need it to be conductive. This could be the kind of option that you'd give here. This stuff, when I Googled it on Amazon, was several $100s for that single bottle. So I would not suggest spending that unless you know you need an issue or you need it for something. There are some things you do worry about in epoxy. You can crack epoxies. You can get bubbles trapped in there. You can have bubbles that get trapped between the material and your sample. Epoxies can undergo beam damage. Epoxies in particular, they're an organic compound. They will interact with the environment in your SEM. They can degas. If you are trying to measure water contents in a very dry sample or carbon contents in a very dry sample, if your sample has been put in epoxy, you are out of luck because the epoxy will degas more water and more carbon under a vacuum than the material you want to measure. So if we want to measure water contents in a moon rock, which is a thing that people measure, you cannot epoxy mount your sample. You have to come up with other things. They have creative methods of using a soft metal and embedding the sample in a soft metal piece of indium or something like that for those types of measurements. All right, this I stole from a lab in the UK, is a list of 20 some different epoxies and what they measured on each of them. There's an overall score. Some of them give a higher hardness. Some of them have a more quick cure time. Some of them are more effective at relief on surfaces. Some of them are more effective for viscosity. Some of them, this is a lab that had too much time on their hands, first of all. But if you're running an ion probe lab, you really care about some of these properties because you really got to, you're mounting 1,000 zircons and you want to make sure you do this correctly. So you spend your time making sure you know what you want to mount things in. Why does our lab use the epoxy that it does? And this is the answer in literally every lab I've been in. Don't anybody want to guess? The answer is somebody else bought the stuff. And it's what we have because somebody else bought the stuff. Meaning that whatever decision tree went into it, long since passed. Could be what the supplier recommended, could be what was cheapest, could be what was available at the time. That's literally in every lab I've been in. The main answer to that question is, we just use what we've always used. If you really needed to care about something, there's a lot of people out there who have spent their time doing this to figure out what is best to use in labs. Mineralogists and petrologists will occasionally have discussions over what epoxy is used where and why. They are tedious because, well, it's epoxy. If your sample was the simple one and it's metallic, you may just be able to attach it to your stage or connect the metal to your stage even if it's mounted, and boom, you're good because the metal will just carry away any current and you're set. With less conductive material, you might get away with measuring your stuff even if it's unprepared or uncoated by using variable pressure mode, or if you don't zoom in to highest magnification, you might be able to minimize charging that way. That may make it so you can't use secondary electron imaging. Okay, we've covered that trade-off already a few times. All right. Irregular, rocky, powdery, or biological material. Taking material that's been embedded and exposing it at the surface is typically necessary. And then the next step will be coating it in something conductive so that your charge can be carried away. To highlight, why would we embed something in epoxy or a similar material? Prevent motion, to enable BSE imaging, including through slices of materials, and eventually to do proper EDS or high resolute or high precision WDS, which is microprobe measurements. Those are the reasons why we might embed something in epoxy. What are the downsides? Once it's in there, it's in there. It is nearly impossible to get stuff out of epoxy if you put it in there. There are some very aggressive chemistries that can attack epoxies. They will often damage your sample, and they will almost, even if you use one, you'll still leave an epoxy coating on the outside. So if your sample is a piece of a returned asteroid and you are going to coat it in epoxy, you better know that for the rest of its lifetime, this extremely rare grain is going to be okay mounted in epoxy. And it will limit some analyses. If you are trying to do certain types of isotope work, if you want to do carbon isotopes on your sample later and you're going to mount it in epoxy, you're not doing carbon isotopes on the sample later. So this is what I mean when I say think through the analysis you want to do beforehand. All right. Then we say, now we got to get our sample to size. You may have to cut it. There are saws, grinders, break stuff. All these things are tools you may need to use. We have a low-speed saw in our building. They are diamond impregnated, so they can cut through nearly anything. Tweezers, files, brushes, dental tools, knives, but you get the idea. Now, we take our rough sample, cut into it, want to make sure we have a relatively smooth surface, because if this is the surface I've cut into, it's still pretty rough. If I try to do an EDS analysis right there, I'm not going to get a signal. And if I'm trying to do backscattered imaging, I have the same problem. I can't actually see anything because the surface is too rough. So here, we gradually grind down the sample to a better and better polish, flattening it and making it so that the backscatter signal is literally coming from a flat surface at every point. Same thing with the EDS signal. It's now hitting a flat surface, hitting a controlled volume, and coming back up. Who has not done this before? Has everybody else polished a sample before? Not, or, okay. So we'll get a chance to do this a little later, okay? Giving you the intro now. Basically, this is like doing with sandpaper. You go to gradually finer and finer grits, and that will improve the polish on the surface up to the point that you get a nice cross-section across your material. When you're doing this, stick in the back of your head that the bigger the number, that's number of particles per unit area. So bigger numbers is a finer grain size. There are numerous devices for doing this. There are ways to do this in an automated sense. This one is a dimpling grinder. If you want to see a video of it, you can load the video up later. I'm not going to do that. But yeah, this takes some effort. We're going to do it by hand, because I usually do it by hand. But there are automated tools that can do some of this work for you. There are other sample preparation types. The one on the right is a sandblaster. So this is literally, we're going to grind into our sample using sand. Here is acid etching. So we've polished a sample here, and we gradually allow that surface to react with acid. In this case, we're dissolving the stuff in between crystals so that we can get the texture of the crystals there to show up better. In all of these, we have one particular problem. When I'm grinding something, if I'm doing mechanical abrasion, meaning grinding it, hitting it with sand grains, whatever I'm doing, the surface environment is an unstable environment. If I'm grinding this, even under water, even under liquid nitrogen, the friction of grinding two things together creates heat and creates distortion, and creates the opportunity for chemical reactions to happen. So if I'm polishing a sample, there will be a nanometer to micrometer thick layer of damage at the surface called a BLB layer. It will contain both remnants of whatever I've polished it with, water from the air, carbon from the air, oxide, where the material that I've exposed has reacted with the air to form an oxide layer. And then this set of layers right here that is the same stuff, but has been either distorted or even turned into a glass. This happens just from polishing. That's the amount of damage that happens. It does not penetrate deeply into your material. This layer is shown as nanometers thick, whereas the analysis volume of a microprobe or SEM is micrometers thick. But it can be important because if we're trying to measure details about the structure, any damage that's been done to the structure is going to affect our analysis. For certain types of measurements, there's one we'll talk about tomorrow probably called EBSD, done on many electron microscopes. It's called electron backscatter diffraction. It's a technique that you use the microscope on a mineral to determine its orientation. If that surface layer is showing damage, then the original orientation has been affected by whatever damage you've imposed on it. So if you're trying to measure the precise orientation of, in steel, of two different crystals of the steel, because the offset between them is really important for the strength of the steel, and you've imposed a 2 or 3 degree damage zone on the outside, that'll carry through to your analysis. Cleaning up that layer becomes very important. There are ways to do that. This sample here was polished in colloidal silica, meaning we took a previously polished sample, to the finest we could get, put it in this extremely fine slurry, and let it vibrate around in that. Usually it takes a few hours, and that will help remove a good portion of that very thin damage zone, making it easier to get a good analysis there. It's nice, it's super high quality, but it's also super fine stuff. If you're immersing this sample in superfine silica or superfine aluminum, you're going to get some superfine silica or superfine aluminum in your sample. I have run into this before where it has affected some analyses I've wanted to do. Some more interesting modern techniques that we're not going to do in this session, but I'm going to cover, include focused ion beam preparation. Has anybody done this before? Are you familiar with this one? Okay, she was prepping this for herself this morning. Okay, a focused ion beam is, here's my sample. I create a beam of ions. I slice through my sample and create an extremely thin, extremely small piece of my sample that I often will move around inside the microscope. So many of these are actually either directly attached to a scanning electron microscope or a transmission electron microscope. You literally slice the bloody thing off, use a micromanipulator inside the machine to grasp the piece you broke off, and take it over to your sample tray. For transmission electron microscopy, where you're literally blasting a beam through the sample and almost effectively seeing individual atoms, this is often done because you want a very thin sample to blast electrons through it. SEM it is done sometimes because you can get a nice fine slice through something, and if you're trying to expose a single crystal that's right in there, okay, slice through this, and now I've got that crystal exposed. Now I can manipulate it inside the SEM. These are not cheap. This is the definition of not cheap. So you've got an ion beam that you're firing inside a vacuum chamber to burn off a piece of the material, then grabbing that, moving it up to your sample stage, all while done under vacuum. You're not going to learn that in 4 days. Okay? If you ever have to do this, you know who's probably going to do this the first 10 times is going to be the lab manager. And maybe they'll coach you up for this on their specific machine. Okay? It's powerful. It's done. It's terrifying. Okay. The other one that's on the list that you might actually be able to do at some point in your careers is ion milling, or over at Johnson Space Center they call this their next generation sample preparation system. Instead of grinding a flat surface by abrasion, this one uses an ion beam coming in at an angle to gradually ablate away atoms from the surface. So we have kind of our specimen that's on a spinning stage that rotates around. We fire ions in a controlled angle at this, and that gradually ablates away any surface damage area. Okay, here is from a fib section with an amorphous zone right at the tip from when that was cut. This is a similar surface that has been cleaned by ion milling. So down to, what's my scale bar here? 20 nanometers, okay? I have cleaned off a 30 nanometer thick zone to make this work. Now, does every analysis need this? No. But if this is important, if I need on my microscope or to get down to sub-micrometer resolution on a surface, this is a technique that can give me a very finely prepared, low damage surface for orientation analysis or something like that. These were 2 images done on our electron microscope of these are similar materials, not the same zone. Okay, same materials. They were prepped in 2 different ways. This one was prepped by standard polishing. This one was prepped by ion milling. Which one is more porous? This one, right? Is that porosity real? We think it probably is. This is coming from a chondritic meteorite. There's probably some amount of porosity in between the grains of these things. When we just polish this up by hand, we get a great image of all these. We get a nice cross-section of everything. We are potentially losing a detail. If this porosity is real, and one of our postdocs is exploring this right now, this porosity could be something that we're losing the understanding of when we do a standard polishing step, where we mount everything and lock it in place. The ion milling at an angle, shooting a beam there, if there's porosity in the sample, it will preserve it in a way that we can actually see it and characterize it. Okay, so we've now done all of our grinding, all of our polishing, all of that work. Now we have to clean it. We have to remove anything that could compromise the SEM, anything that could compromise the sample, anything that might get in the way of our chemistry analysis. Stuff we might need to think of include dust. They include the polishing material. They include hydrocarbons, such as if I touch the surface of my sample, I have just added some hydrocarbons because my skin has a little bit of oil on it. And other biologic contaminants are a big problem as well. What kinds of things do you do? Burst of air, brush it. Cleaning in various solvents, depending on the material, is usually the next to last step. And I've already kind of gone through that. Okay. Then we want to deal with some version of a coating. Need a coating on there to remove the current. I liked this one. This is an SEM being set up to analyze the pages of a book. In order to limit charging, they have wrapped their book in aluminum foil with the part of the page they want to analyze exposed here. This is actually a doable thing. If you are analyzing a sample and you just have no other way to get a conductive surface on it, you can poke a hole in aluminum foil. The foil around it will drag the current away, and it'll keep charging from building up at your single spot. Applying a thin coating of some type of evaporated material to allow current to be carried away is the standard technique that's done. You then, once this material is coated in your substance, you hook it to this stage in the SEM, and now you have a direct electrical connection that can carry away charge. That's the usual setup. Well, deciding what to coat with is another question. Are you trying to do backscattered imaging? Backscattered imaging is a very common thing on an SEM. It responds to the atomic number of the substance that's right at the surface. What happens if you coat your sample with gold or other heavy metal? Well, you're applying something with a very high Z number across the surface. This is going to make it harder for you to get a backscatter signal. You'll still get some because the thickness of the coating layer should be small, but it's definitely going to affect the backscatter properties. On the other hand, our Tholen victim back here. If we're trying to analyze a carbon-bearing compound, can we coat it with carbon? Probably not. That's just not going to work. Does the cost matter? Sometimes. Which more expensive, graphite or gold? Slight difference in cost. So if you're going to coat something with gold, you better know why you're coating it with gold. It's another one of those think through what we want to analyze steps. The way we're going to do this here, we pump down the pressure on a sample so that it's 1 × 10⁻⁵ atmospheres, maybe something like that. Have your sample moving so that it's not just going to coat one side. Make sure you're covered in safety gear as needed because this can affect your eyes. You run a current across your material, evaporate it, and allow it to precipitate onto cold surfaces. Then you allow it to cool off. A few notes here. If you're coating something with a metal alloy, there is no guarantee that what will precipitate on your sample is what you start with. So if it's just gold, then it'll be gold coated. But if it's, a gold palladium alloy for whatever reason, there's no reason why the thing that precipitates on your sample has to match what evaporated. There can be a fractionation in on there. All right, and I might even hesitate to do this on our Tholen sample, even if I wanted to, because to get this to vaporize, I'm going to have to heat the stuff. Could that cause vaporization from my sample? Most definitely. I have a picture of this thrown in. Everybody knows what this is, right? James Webb Space Telescope. How do we get those plates gold? They are sprayed with this in a vacuum chamber. You take the plate, you put it in a vacuum chamber, you pump down to a high vacuum, you run a current across gold that vaporizes the gold and deposits in a thin layer on your mirror. That is how those mirrors were designed. Any of the telescopes you ever go to will either be out in space like JWST, if it's one of these mirrored ones, or they'll have a room where they can clean and repair one of those by recoating them. Is this my last slide? Oh, 2 more slides. A couple more slides. All right. Other things to think through. When we're thinking about sample prep, we do have other tools to limit charging. If we are analyzing a sample and we see charging, we covered changing the vacuum mode earlier. You guys may get to experience that on RSEM. We also have the current and accelerating voltage settings. If we are having a charging problem and we drop the current, could that reduce our charging problem? I have a problem with too many electrons. What's my solution? Fewer electrons. Literally, that is the logic. If the electrons can't escape, I have fewer of them, they might be able to escape. Accelerating voltage is how much energy do the electrons have when they hit the sample. If I drop that, then the electrons that are in the sample have less energy. They may fluoresce less. There is no single version of this that works for every sample. In general, we started an hour ago with the statement, what are we trying to analyze? How do we get to that analysis? That is, at least to me, the way to think through this. If I'm given something that's new or interesting, I start assessing, what is it? How do I get to the analysis that I want? And there's weird things you can put on there. These are cells. I have no idea what they did for sample prep on this, but you can get weird stuff onto an SEM. Biological materials, powders. Always think through your analysis before you try any sample prep. If it's powder or loose grains, how do I anchor it? How do I avoid charging if the material is not conductive? Do I care about the chemistry of it? Because I might not be able to get an accurate chemistry if it's a powder that's unpolished. If I polish it, do I care about the orientation? Do I care about the surface features on this? For biological materials, are they anchored properly? Are they stable under vacuum? Is charging going to be removed? There are weird analyses done on thin films for material science purposes. And in these cases, you have to understand the conductivity. You have to understand what the material is you're putting it on. All sorts of other things you can go through. Here's a diatom, little fine shell on a silica test from the ocean. On the left is uncoated, on the right is with a gold coating. Notice the difference in charging, but at the same time, we've also kind of reduced the signal a little bit from there. Here is high and low vacuum mode. The one at the left is a charging disaster. The one at the right is low vacuum mode. So this is high vacuum at the left, taking it to as low a pressure as possible. Exact same material on the right with the vacuum pressure reduced. Okay, that is an overview of sample prep. Okay, now I'm going to stop recording here in a second, and we're going to walk down the hall, and we're going to actually start doing some attempts at sample prep. I have a whole bunch of stuff we can work with, and we can also start trying to figure out how to best deal with the stuff that people brought. Okay, you need to take a restroom break, take a restroom break right now. We'll meet, everybody remember where the sample prep room was? Okay, we'll meet there in like 5 minutes, okay?